Now, let's welcome our first speaker, Dr. Roberto Calandra from Facebook AI. So Dr. Calandra has got his PhD from TU Darmstadt under the supervision of Professor Ian Peters and Professor Mark Dennismore, and he did a postdoc at UC Berkeley. And he has been working on the conjunctions of machine learning and robotics. And he did lots of works related to reinforcement learning and manipulation, and also the combination of tactile sensing and manipulation. So now, let's welcome him.
Thank you, Wenzen. I'm gonna start sharing my screen. Please let me know if you can see. Can you hear me?
Yeah, works well.
Okay, perfect. Okay, good morning, everyone. On this side of the Atlantic was a fairly long night, so I'll try to keep it short and to the point. Today I'm going to talk about some of our recent work to trying to move towards in-hand manipulation from vision and touch. And just to give a brief motivation, I'm essentially going to start from the usual why is touch important. And touch sensing is a crucial sensor modality in humans, as it is the only sense that directly measures contact forces and thus interactions with the environment. And in a world dominated by Newton's law of motions, most motor control tasks are best represented and understood in terms of balancing of forces rather than joint positions. And as a humans, we all have experience of how extensively we use touch with sometimes barely realizing it. So if our glass is slipping from our fingers, we will automatically like grasp it. We use touch for measuring the mass of objects to distinguish between different materials, as we have seen just now, or even in the dark of, in our night to search for our phone without having a light on. And you already seen this video earlier today, but I'm going to play it again. The importance of touch is also fairly well understood for humans' motor control. And in these videos from Ronald Johansson at the University of Umeå, they essentially demonstrated how familiar motor control tasks, such as lighting a match, can suddenly become extremely challenging when we are deprived of our sense of touch. So in this case, it took several times longer to do it after losing the sense of touch. Now, also in robotics, it's fairly well understood, and of course, otherwise there wouldn't be this workshop, sort of thought that touch is a crucial sense that needs to be integrated before we can really deploy robots outside of structured industrial environment. For example, in houses or in our society, where we also have interactions with humans. And for example, some of our work we did several years ago, we had these two images, and we wanted to evaluate what is the stability of a grasp. And just from pure vision, these two images are virtually the same. It's almost impossible to distinguish which one is a successful grasp and which one is a failure. On the other hand, in the moment when we measure forces, it's very easy to disambiguate between the two, because on the left we will see that we have no contact forces, while in the right we can see that both fingers are applying some force to the object. So in my mind and in practice, integrating touch sensing in robotic manipulation platform have been proving very challenging for at least the last 20 years. And there are two main challenges that needs to be addressed before we can really deploy touch sensing at scale in the real world. The first challenge is the lack of good available tactile sensing hardware. And the second one is the difficulty of integrating touch into traditional analytical control schemes. In particular, in the moment when we start having very high dimensional tactile inputs with thousands or hundreds of thousands of covariates. So if we look at the literature in tactile sensing hardware, we all know that it's a gigantic literature. There are hundreds, thousands of papers, and here there are just shown some of the most recent ones. But what strikes as peculiar is the fact that most of these sensors are effectively prototypes that will never leave the labs. And if we look at actual commercially available sensors that can be built or bought, there are very, very few of them. Biotech is probably the most known exception. You can actually buy them commercially. They are mass manufactured, and that's very cool from a researcher perspective, because I can just go out there and buy one in theory. However, if we look at what are the important metrics for tactile sensors, there are several metrics that are really relevant. One of them is, of course, availability. Another one is cost, especially if we want to deploy these systems in the real world in that scale. We, of course, would like sensors to be as cheap as possible. Form factor is another important thing, because some of these sensors are bulky or are still relatively big, and instead we would like to have ideally sensors that are as small and as nimble as our fingers. Then there is what are the actual capabilities of the sensor. Some sensors provide single contact points, other sensors provide vector forces, other sensors provide topological maps, and effectively these capabilities might vary depending from which application we care about and which sensor we are going to use. And finally, reliability is a major point. As a humans, we can essentially go throughout our entire life with a single hardware, with a single finger, without never changing it. And in practice, for most tactile sensors that we have nowadays, they are fairly limited in terms of how many contacts we can make, how many objects we can grasp, how much force we can apply before they break or before they need to be recalibrated, and so on. So today, as a step toward enabling more researchers access to good touch sensing hardware, I'm going to present you Digit, the first mass-producible, low-cost, high-resolution, compact tactile sensor. Digit belongs to the family of vision-based tactile sensors and consists essentially of an elastomer, RGB LEDs, and a camera, where the formations of the elastomer are recorded by the camera as changes in color cues. These principles, which you've already seen in other sensors before, allows to generate rich high-resolution images of touch easily and without any moving part, with a sub-millimeter resolution and tunable sensitivity, depending from what type of elastomer you decide to use. Moreover, if the elastomer is equipped with markers, it also allows measuring shear forces, which seems to be an important information for many manipulation tasks. Now, what differentiates Digit compared to other sensors that have been published before is that Digit was designed from the ground to achieve three major goals. The first one was to have a form factor compact enough such that the sensor could be mounted on a multi-finger hand. The second goal was to have a high reliability to support large-scale data collection with hundreds of hours of interaction with the environment. And the third goal was to have a sensor which is easy to manufacture and to maintain. To achieve these goals, we developed Digit to be modular and also to use high-quality sensors with custom controllers and electronics and firmware. This enables the manufacture of the sensors through standard 3D printing tools and provide a path forward to scale up to mass manufacturing potentially. Compared to previous designs, Digit provides an easy-to-use platform with increased durability and serviceability overall. And in addition, our custom firmware allows for lightning control in full color RGB and enables frame rates up to 60 FPS. Just to give a brief comparison against what is probably the best tactile sensor, which is commercially available today, which is the BioTac. Both BioTac and Digit are compact sensors designed to be mounted on multi-finger hands, such as the Allegro hand from Wonic. However, while the BioTac provides 29 points of contacts, Digit has over 300,000 points of contacts. Moreover, while BioTac costs approximately $10,000, Digit can be manufactured for $15. Finally, part of the scope of this project was to lower the bar for doing research into touch sensing and really provide researchers a reliable platform for doing their own research on touch sensing. And for this reason, we open sourced the design of Digit, which you can find at digit.ml. And this includes mechanical files, include electronics, includes firmware, binaries of the firmware, and a Python interface. So looking a little bit more into some of the improvement that we did in this sensor, I want to start from the elastomer. In parallel to the sensor, we also developed a new process for manufacturing elastomers in a more reliable and simple way. And while our elastomers are slightly more transparent to external light, they are also order of magnitude more robust compared to other elastomers. Here there are images before and after 5 passes with a standard abrasion tool. And what we can see fairly clearly is that while the other elastomers have significant degradations in their surface, our has no visible degradation, which is of course great. In addition, our sensor is designed to be very modular, so that even if an elastomer breaks, it can be rapidly changed in less than a minute by removing that one single screw. And once you remove this screw, you can essentially replace the whole elastomer at once, very, very fast, with a sort of push and click mechanism. This also allows to in practice, tune the sensor to the desired applications. So for example, you might want to replace the gel, the elastomer, with a harder or softer one, depending from how much sensitivity you require or how much force you plan to apply. Or you can also changing altogether the family of elastomer coating that you're using. So for example, here there are images taken from a Digit using elastomer with different coatings. Starting from the left, there is a purely reflective coating for accurately measuring surface and texture. In the middle, there is a reflective coating with markers to compute optical flow. And on the right, there is a transparent elastomer with markers, which are barely visible, unfortunately, in this picture, to control finger position during grasping. A little bit similar to what finger vision does, if you're familiar with this other sensor. And in practice, this allows a lot of flexibility because you can have the equivalent of several sensors in one, depending on which elastomer you decide to mount. Now, after designing the sensor and manufacturing, we also decided to demonstrate its capability by tackling a fine manipulation task. And here on the right, you can see a Wonic Allegro hand provided with 4 tactile sensors, Digit tactile sensors. And in practice, we know that characterizing and processing the rich high-dimensional measures generated by 4 Digit sensors would traditionally be very challenging for traditional control scheme. So we decided to use more advanced machine learning techniques to integrate digits into the control loop of our hand. And in particular, we selected as an example of fine manipulation task the manipulation of a marble between two fingers. Now, this is a very challenging task that for a robot require a significant amount of fine control of the contact forces, especially since the elastomer is not a rigid surface and is also a little bit curved, so it's actually really difficult to control this. And in our setup, in particular, we consider the control of two fingers, the thumb and the middle finger, for a total of 8 degrees of freedom for each finger, being controlled directly from raw tactile measurements collected by the two digits. And we started by setting up an autonomous self-supervised data collection pipeline where the hand would autonomously pick the marble and apply random actions to the fingers. And eventually the marble would slip down from the fingers of the robot and would fall into this red basket where it would settle after a few seconds in the middle. And at that point, we had a linear actuator that would push the marble back up, where the end would pick it up for the next episode. And sort of in this way, we could almost completely autonomously collect several hours of data collection for a total of 4,800 trajectories trials. Now, unfortunately, you might have noticed that this is not a video of the final results and the final sensor that we published, but because of COVID, we didn't have access to the setup anymore after, essentially after publication, so we couldn't collect any nice video, unfortunately, and this will also show later. But in practice, for the as a model, we decided to perform how to control this task. We decided to use a model-based approach where we learn a forward dynamics model of how the marble will react to potential actions, and then we will integrate this into a model predictive control setting. So the dynamics model is learning in a two-stage fashion from raw tactile inputs, where we first learn an autoencoder network with structural bottlenecks that essentially extract the XY position of the ball of the marble plus the amount of force that is being applied to the marble. And once we have this low dimensional feature space, we can now learn a dynamics model from this latent space that, given the features from the two fingers and the potential sequence of action for the 8 degrees of freedom, all the 8 degrees of freedoms, predict the next state. And once we learn this dynamics model and we train it, we can use it to predict the consequences of our action in the long term, and therefore we can control our robot using a model predictive control by continuously replanning what is the best sequence of actions to apply, and then applying the first one. The results also seems fairly convincing. So here we can see that our learned system significantly decreased the distance between the initial points and the final, the desired goal in tactile space, while if we compare to a PID controller, the PID controller is instead very, very difficult to tune because it's very high dimensional. And even after spending a significant amount of time trying to tune it, our learned system still outperformed the PID controller. Now, something that we also notice is that our system does lose marbles occasionally. So we have a failure rate of about 25% of marbles dropped, which is mostly due to the really difficult nature of the contact. So typically what would happen is that one of the fingers would just apply a little bit less force, and then it would lose the marble. it still outperformed PID controllers, but we also believe that collecting more data would essentially improve this and reduce it down with enough time and data. Unfortunately, I do not have any video to show you of the final policies on the hand because COVID impacted our lab operation while I was having vacations in Italy, so I couldn't take any final video. However, I can show you some manipulation sequence in the touch space, and here sort of the temporal sequences from the left to the right, where the green dots is the initial position of the finger, of the marble in the finger, and the red is the desired final position that we want to achieve. And we can typically see how as sort of time passes, indeed the position of the marble moves and becomes very close to the desired target position. So this was a gigantic, the overall project was a gigantic effort, and DIGIT would have not been possible without the contribution of an amazing and diverse team of people that did a lot of work, starting from the hardware design, the manufacturing process, the learning algorithm, and the experimental evaluation. So I want to thank them all. Now I'm almost out of time. I just wanted to point out that in parallel to DIGIT, there is another project that I care about, although I don't have time to talk about this here, which is another sensor called OmniTact, which designed at UC Berkeley. Now, the difference to DIGIT is that DIGIT was designed to be a sensor that can lower the entry bar to touch sensing research, while this OmniTact was more a way of developing a new prototype of high-end tactile sensor to test some new concepts of how to design this. And in particular, the goal was to develop a sensor more similar to a human thumb in terms of capabilities, such as being omnidirectional and being even more compact. The main novelty that I want you to carry home here, which is worth mentioning because it's different from GelSight or DIGIT, is that here we cast the elastomer directly onto the cameras, onto the 5 cameras of the sensor, and this really allows to shrink the form factor because we can shave off that 1 or 2 centimeters of empty space between the camera and the elastomer, and we can also remove the transparent support. And we also get nice images. We have a robot experiment, so you should have a look at this paper. So to summarize and to conclude, I think that touch is really a key sensing modality for interacting and sensing with the environment. And today I presented DIGIT, which is the first mass-producible, low-cost, high-resolution, compact tactile sensor. And we demonstrated his capabilities by learning a challenging marble in-hand manipulation task from raw tactile readings. And something that I think is very cool is that DIGIT is actually open source. So if you go to digit.ml, you will find all the mechanical files, electronics, binaries of the firmware, and a Python interface. Tomorrow, the paper will also be posted on arXiv. It's already posted on IEEE, but on arXiv, it's going to be more accessible. And in the next days, we also plan to publish CAD files for 3D printing adapters for DIGIT for the most common parallel jaw grippers on the market. If you are interested in knowing more about DIGIT, please come to our poster on Wednesday. Unfortunately, we cannot give live demos as we originally planned to, but we'll still come up with something nice. And if you want to know more about OmniTact, please come to our poster on Monday. In future, we plan to use DIGIT for studying perception and control aspects of touch, and in particular, in-hand manipulation. And overall, the grand vision that I'm interested in studying and sort of nailing down is how to try to reach human-level performance in manipulation by using machine learning to integrate vision and touch. So thank you very much for your time.
thanks, Roberto, for sharing. So the audience are very interested in the sensor. It's really a nice one. And especially people want to know, is that possible we can buy one for $15?
We do not produce at the moment or plan to sell Digit. We do open source it. So if you want, you can build your own, I guess.
So I guess everyone can use your CAD file and software design to make their own sensor?
Correct. All the information that we provide in the open sourcing allow anybody with access to a making space to build its own. In practice, you just need a 3D printer. You can order the electronics online from China or wherever you want. The only thing that is a little bit more subtle is the production of the elastomer, but we also have detailed instruction on how to do this.
Good. So what kind of interface does Digit provide?
So we wrote our own, essentially a Python interface so that you can access the sensor at fairly high speed. And the main interface that we provide at the moment is something like get image, where you get an image out of the sensor. But you can also set some configurations, such as how much light you want to have, what is the intensity of the light for the 3 RGB. You can set what is the frequency that you want, the resolution of the sensor. Oh yeah, the electrical interface is USB, correct. It's USB 2, although we use USB, USB 2B.
Good. So let's thank Roberto again for sharing. So let's move to